Okay.
Others will join soon.
Are you sure? It took a bit longer, unfortunately, because of the traffic. So we didn't eat much and long, but we had a long traffic.
Like 1.5 hours.
1.5 hour traffic, yeah. Oh, yeah, that's there. So we've got 2 hours again, right? Like 4:30. So should we wait for the other people to come,
Yes, I
or
think we
yeah?
can start. Meantime, others will join.
Okay. All right.
I have already informed.
Mm-hmm. Okay, that's good. Yeah, let's just maybe start. I just want to um, just recall what we did in the last lecture. I mean, before we went for lunch. There's only one very simple, of course, very simple kind of relation, which is when you are giving the velocity at one point, like this one, point one, then you have a linear velocity v1, and then what's the velocity of the second point? Then it's of course the velocity of the first one, right? Plus, and now comes essentially because when you're rotating about omega, then it's the displacement vector. I mean r1 2, sorry 1 2 1 2. Yes. So what is it then? Which way? Which way it goes? It actually goes normally like omega cos r1 2. I don't know what happens here. R1 2. Okay. And that's how you. It's a very simple relation, of course, right? So omega is I mean, this is the body, this big potato, rotating. I mean, translating and rotating. And when you have the velocity here, the whole thing is rotating with a certain omega. Then you get the velocity from of point number 2. When you get the velocity at point number 1 by just this simple equation. This is very basic kinematics, and in terms when you now have it all expressed in one particular frame, then of course you just have to transform the omegas, I mean all the vectors, and do the cross product. And the cross product in our new notation is of course v plus, and we have this omega tilde times r1 2. Okay, and if you encode this into a matrix, then it goes like this. So the rotation matrix, I'm sorry, here, the rotation matrix just transforms the omega vector. So the omega itself is not changed. It's just the representation of in which frame it is represented is changed. And then the same is here. So the v vector is of course transformed in the right frame, and then comes the cross product. I mean, if you forget about all these rotations because they are just changing the coordinates, but if you look at what happens to the velocity vector, it's the cross product with omega, and then it's this plus the v and other frame. And this matrix, I mean, this whole transformation of twists, respectively cross screw coordinates, this is termed, I mean, there's a name for it, and it's called the adjoint transformation. It's just a name. Anyway, H is now used to transform twists. That is the message, okay? And that's important because once you have a twist, omega and v, at one frame, you can easily get it in another frame if you have the transformation between the two frames. Okay. And what does it help us for, again, a kinematic chain? Because what we should do in this part is to look into how we get the twist of a body within a chain, a kinematic chain. What we did before is the finite kinematics, as they call it, in a sense that you have finite motions, essentially getting the homogeneous transformation matrices out, right? Which is called finite kinematics because it's finite motions. The sometimes called first-order motions or instantaneous motions, essentially looking at velocities, is the one we're looking at here now. And let's maybe start from an intuitive point of view, in a sense that let's ask, so we have a kinematic chain, right? Again, so we look at body I again, and then of course comes the predecessors, body I minus 1, I minus 2, and so on. And now the question is, just look again, what happens if we are, and again we have revolute joints, what if we are rotating the last joint? So what is and the rest is fixed, right? So we have a certain pose, and this is all frozen, and the only thing that we are doing is now we're actually we're rotating about this, the last joint axis, right? And now the good question is, what's the velocity? I mean, the twist of this frame, which means of this body, due to the motion of this joint. And that's pure kinematics in a sense. Okay, what do we know? Again, we have informations about the axis. So we have the unit vector along the joint axis. That's that one. And let's just focus on this one and on the first part, because this should be somehow omega, I mean the angular velocity, right? So if you multiply this vector with q dot, so again, q is not shown. Anyway, q is the rotation angle. So the time derivative is the rotation rate, so to say. If you multiply the vector with the time derivative of the angle, what you get is the angular velocity vector, right? It's the angular velocity due to the rotational motion. And that's it. That's what we have here. So if you multiply this E, and we express this we express this EI in this body fixed frame. Okay, so we are just, so to say, it's all frozen. We are sitting in this frame, and we are asking what's the angular velocity of this frame because of the rotation of that thing. And I express everything in the frame I'm sitting in, which is Fi. So I express this unit vector in the I frame, multiply with q dot, which is the rotation angle, and I get omega. It's pretty simple. And the same, and another question is, what's the linear velocity? So what's the velocity of this point due to the motion of this joint? If the joint, of course, has a non-zero pitch, then we are traveling somehow. That would be the first part, right? So we are traveling along this EI axis times h times q dot. Essentially saying it's h times omega, right? Because omega is the rotation vector, and then there is a pitch, and the pitch tells you how much you're traveling per rotation. So essentially, omega times h is giving you the part if you have a non-zero pitch, which is the last one. When I say omega, I mean q dot times e, because we said that e times q dot is omega. Okay, but this is for our. If this is a rotation, if this is a revolute joint, this is of course not relevant. What is maybe more interesting is this part. And that's easy because, so we said everything is frozen. The only reason for this motion is the joint rotation. And you get this point, the velocity of this point, again with the cross product. Essentially, what it is, it's like the omega vector, which is e times q dot, cross product with the distance vector. So the displacement vector from here to here, for example, is called BI. BII. It's a bit strange now. What this means is that we are measuring from the frame I to the joint I axis. Okay. Just anyway, so this vector, and what you can easily say is that the velocity of this point due to the rotation of this point is this vector. Is omega cross this vector. You can also say the opposite. It's minus this vector cross omega. Anyway, because the cross product is skew symmetric. I hope you're following me. Makes sense somehow? Okay. So this vector, cross product with omega. And omega, of course, is E times Q dot. Essentially, we are here. So this term, cross omega. Okay, that's more like a super intuitive explanation of how you get the twist of this frame when you rotate about this joint axis if the rest is frozen. Right. And now what about, what about the motion, I mean, the velocity, the twist, the contribution to the twist due to the rotation of this joint? Same. I mean, the argument is always the same. So you have omega, of course. I mean, first of all, you have this vector times q I minus 1 dot. So q I minus 1 dot times this vector is, again, the angular velocity due to this rotation. But we have to be very careful because all these vectors, of course, must be expressed in the same frame. So it's all expressed in the I frame because I'm measuring in this frame. Okay. So we have, so we have for the angular part, we would have, of course, I mean, we would have the omega due to this one and the omega due to this joint. It's pretty simple, I guess. So E1, EI minus 1 Q dot and this one Q I dot. Okay, and the translation is the same. What is the linear velocity of this point due to the motion of this joint? Same. You take this vector and the omega vector and take the cross product. So, and because the vector is pointing from here to here, it's actually omega. It's actually, what is it? Yeah, it's actually this vector cross omega. Okay. So we're always measuring from the frame I'm interested in to the axis. And that is just, a pure kinematic explanation. But what you realize, hopefully, what you see here are screw coordinates, because these are essentially the instantaneous screw coordinates of a motion that gives you the velocity, the twist of this frame due to the motion of the joints. Okay. Yes, that's right. Yes. When I'm saying the instantaneous screw coordinates, what I mean by this is, so instantaneous means they are changing in time. Why are they changing in time? Of course, because if the whole system is moving, the chain is changing, then of course the vectors are changing, right? And everything is changing, right? So these are the instantaneous screw coordinates. And then of course you go on, and then the same argument applies to other joints, and eventually what you get is the twist of the link of the frame I, which is, we call it the body fixed twist. We call it VI, capital VI. It's just the sum of all this. Okay, so that's probably not too difficult to see. Okay, and to make it a bit more compact, we call this vector, each of these vectors, each of them is a 6 vector again, right? This is a screw coordinate vector. We call them J. Simply because in the end, what I want to do, I want to have a matrix that is called J, capital J. And in robotics, you find always these J's. It's all about Jacobians, right? It's like the J's are called Jacobian matrices or Jacobians. And before maybe going there, let's say, okay, now we introduce that vector is J. So we need 2 indices now, right? So we have to say so we have to indicate actually to which frame they are referring, because
Why do we use Jacobian velocity transformation and not in linear transformation? Then we use only transformation matrix.
why I'm using
Here we are using Jacobian.
I'm using Jacobian all the time.
In velocity transformation. But in linear transformation, we are not using it. The term Jacobian is not introduced there.
You mean in linear transformation?
It's for coordinate transformation. When we are giving some joint angles, then we are getting the equal coefficient values of integrity, but
Mhm.
at that time we are not using Jacobian.
So you refer to the linear relation of what? Of
When we are calculating velocities,
Mhm.
at that time we are introducing Jacobian.
Yes, that's right.
But before and for forward kinematics, at that time
Mhm.
we are not introducing Jacobian.
That's right. That's right.
That's why we are using.
You mean so? What we did in the, if I understand correctly, the first one, I mean, the one that you're referring to is the forward. I mean, the what we call the finite kinematics, right? When we use the exponential mapping. That's what you mean, because it's nonlinear. I mean, the mapping. The one that we had. Oh no, it's the other way. Sorry. You have to go the other way around. Yeah. So you're referring to somewhere here, right? So, like this one. Yeah. So the thing is,
Here directly we are using the A5.
well, A5 is just a. Yeah, but A5 is just okay. When you say forward kinematics, in this case, what do you mean? You mean a mapping that gets in the. So the forward kinematic mapping is usually understood as a function, whatever. It takes the q's, the joint angles, right? And they are usually like, if you have n joints, then we have n of them. And what comes out is the end effector pose, okay? And let's say that we have n links, then we have this. And this is an SE3 matrix, right? This is an, oh, it's too much drawing here. Anyway, so this is what we call the geometric forward kinematics problem. And as you see, this is nonlinear. I mean, this is highly nonlinear because the dependency of this formula, if you call this f, this is my f that I have there, and the dependency is nonlinear in Q, right? Because the exponential is some nonlinear function. So and a Jacobian is always a linear relation, right? The Jacobian is always, so the Jacobian is actually the coefficient matrix in a linear mapping. Maybe you should make space here. Oops. Yep. Okay. So the geometric forward kinematic problem. Forward kinematics. So essentially, what you, as I was saying, right? So you have the Q's, which have all the Q. I should write better on my black whiteboard. So Q1, and then you have up to Qn. Okay. So this is what goes in, and what comes out is the f of Q. So an f of Q is H. I mean, the homogeneous transformation from n to the ground. And this is where we have the exponential mapping, right? So the velocity forward kinematics problem is a bit different, because what it is here is they're saying what goes in is Q and Q dot, right? And I'm sorry. And what comes out is the velocity. And how do you get the velocity? The velocity, so V0n, we just called it Vn, is equal to, and now comes this Jacobian. We say there's a Jacobian times Q dot. And this is it, because the Jacobian always is the coefficient matrix in a linear relation. And when I say linear, it is linear in Q dot. So that's why we have a Jacobian there. And actually, this is why the Jacobian, why this is called the Jacobian. What is a Jacobian? I mean, generally speaking, mathematically, what is a Jacobian? Correct. It's a partial derivatives. And essentially, if you say there's a mapping that depends on Q, but it's a function of Q dot, then you take the derivative of this mapping at the partial derivatives, and this is essentially this J, the Jacobian. because it's the partial derivatives of that equation, of this relation of v as a function of q dot. I'm not sure if this answers your question. Maybe? Okay. Yeah, so and that's it. Okay, so what I was saying is for this, so now we have vector, 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 vector. We have n vectors, right? We have n 6 vectors. N because we have n joints. Yeah, now we have I joints. Okay, maybe to not confuse you. We are generally looking at the kinematic chain comprising n bodies and n joints. Now I stopped here because this is like, I stopped at body I, right? But of course it goes on till n, right? But for each of the bodies, I mean, for each link, I have that relation, correct? So this I goes actually from 1 to I. So you can have the same expression for, 1, 2, 3, 4, up to n. Why I'm saying this? Yes, so I'm saying this, so we have two indices. One is the body to which we are referring to, of which we are getting the twist, which is I. Okay, that's fine. So this is the whole thing. But each of the columns, of course, refers to a joint, right? This is joint 1, joint, and so on. And the twist of body, the velocity of body I, of course, only depends on the joints 1 to I, right? Because whatever comes after this joint doesn't, I mean, after this body, or the joints after the body, they don't influence the velocity of the body, right? Because it's all fixed to the ground, and then you have to change. Right. So what I'm saying, so yeah, so each of these columns gets a name. The name is Ji, and then comes the index of the joint. Okay. So and then to make life easier, we define a big matrix, and that's essentially. By the way, you're getting these slides again. Yeah. But anyway, and then to make life easier, so we put this all in the big matrix, and that's actually the Jacobian you referred to, right? So because the whole matrix is then called the Jacobian matrix. Before coming to the name, and of course I was saying we have of course n joints in the whole linkage, right? In the whole kinematic chain. That means that eventually, because I was saying that we have this vector q, right, comprising all the joint angles up from 1 to n, we of course have to have n columns, right? Because you're multiplying with an n vector, so we have to have n columns. Even though the last I plus 1 and so on, they don't influence, that's why we have zeros. Okay, fine. So we have one Jacobian. This is the geometric Jacobian of body I. So you multiply this, exactly. You multiply this here with the q dot, and you get a twist out of this. In literature, you find the term geometric Jacobian. Have you heard about it? Geometric Jacobian? No. It's simply saying that, as you correctly said, I mean, the Jacobian normally is, the partial derivatives and so on. Have you seen me taking partial derivatives? No. So because it is a purely geometric construction, you only take vectors, again, like in opposite to the DH parameters, you only take vectors and some cross product operations and only geometric operations, right? There's no partial derivatives in here, which makes life easier because you don't need partial derivatives. You don't need symbolic algebra, whatever stuff you normally use. And that's why it's called geometric Jacobian. Of course, it is the same as if you would take the partial derivatives, right? You can do this, but yeah, you don't need this. Okay, good. Yes. What else to say? Wrong direction. Yes, and I was actually saying that these are apparently screw coordinates, right? Because it's the same structure and apparently the same construction to get these columns. I mean, these 6 vectors, as we did before, because they are actually screw coordinates, but they are depending, of course, on the poles of the system. Because if the system is changing, these vectors are changing, right? No. these vectors are changing. And that's why they are the screw coordinates. And in particular, these vectors here, let's say this one, for example, is the screw coordinate of this screw motion according to the joint I expressed in the frame Fi. And of course, the same is with these, right? But they're instantaneous because they are changing. I'm repeating myself, I know, but that's the way it is. So now I was saying that I erased it already. What I was saying at the beginning of this second part, I was saying actually that when you have screw coordinates in one frame, or let's say twists in one frame, you get them in another frame by using this adjoint transformation, this 6-6 matrix. Okay? And if this is true, you should actually be getting this these instantaneous screw coordinates, that one, from the ones that we measure in the zero reference configuration. Because we did the same actually. Remember how we came up with these x vectors, with these screw coordinates, the body fixed screw coordinates was exactly the same construction. But the only thing is that we said, okay, now this is our reference configuration, like a cat drawing or something. Okay? And we called this B, we called it X. What's the difference between B and X? Simply because B for Q equal, where's Q? For Q equals 0, so the joint angles, if you say all the joint angles are 0, then the B becomes X. In other words, we should be able actually to transform these originally computed X in the reference configuration into our J's, our joint Jacobian columns. And that's true. Because you only have to do is to transform them from the initial configuration to the current configuration. That's it. That's it. Maybe. Okay. I would claim that BII is equal to XII. I know, it's a lot to take in, right? What was XII? XII. So what I'm talking about, maybe I should write it again just to remind you, because it was before lunch, and lunch normally kills all the memory. If you have the screw coordinate of the joint I, how was it constructed? It was X, it was the unit vector EI, and it was EI, no, it was P. It was, yeah. So it was the unit vector, and then it was the cross product. Oh, again. I'm making all the mistakes you can make. So it was XI, cross product EI. Okay? So this is, I guess, how it was. And all of them were represented in the frame I. So this little I, this is a little I here, what was it? It was the vector from the frame Fi to the axis. That's how we constructed the screw coordinates. Now, again, we are rigid bodies, right? So this vector, I mean, in particular, the BII, so the one that goes from the frame I to the joint I, is constant, because this is not changing. If the whole thing is moving, right, this is constant. Okay. Very nice. Very nice. What else can I say? Yeah, what is this Hij doing? Hij transforms from the J frame to the I frame. Okay. Yeah. How to explain this? So the screw coordinate vector xj was the one, I mean xj or xi, or xi, I mean this one here, is the one that we, as I was saying, constructed out of this picture here. And this is constant because x is constant. In order to transform this screw coordinate vector into a different frame, and the frame, yeah, See, now it's a bit of a problem because because I should have J here and I. Anyway, let's say this is J, right? So I want to transform this into another frame I. Then the only thing I have to do, I have to apply this transformation. What is the frame transformation? It's Hij. So, and then the only thing that I have to do, I have to plug this into the adjoint transformation because this transforms screw coordinates. So these are screw coordinates in the J frame, and now I get them in the I frame, and this is what I need because I need. What is this for this one, for example? This is the screw coordinate of the I joint of the first joint expressed in the I frame. This is the screw coordinate of the I-1 joint expressed in the I frame. Okay, and this is exactly what I'm doing. I take the screw coordinates of the respective joint, which is constant, and transform them into frame I'm interested in, which is the I frame, and that's it. So essentially what you're having here is, and there's of course a different way of explaining it, but this is the one that's probably most easy to understand. What you're having here is like, again, a geometric construction because you could have asked, okay, if this is all changing in time, how do I get the B's and the E's? I mean, still you would have to somehow compute the vectors because they are changing. Now, this is the way to do it because the X vectors, I mean, the screw coordinates, this is what you have to do anyway. And you have seen how easy it is to do because they are constant. You take this from the zero reference configuration, this is done. And then you construct your H matrices because this is what's come out of the product exponential formula. And now you can use all this to get the columns of the Jacobian. And that's where we are. Okay, what is this? Yeah, and that's full stop. So this is how the Jacobian is constructed. Good. In the slides that you're getting, I left this part, which I'm not going to, this is not my intention to bombard you with this. But this is the mathematical explanation for it, to derive it analytically. If you have time and interest, you can go through it and we can maybe discuss it, but I'm not going into detail here. You will have it, I left it in the slides and you will get them, okay? So this is the, okay, so maybe we have to skip this. You don't see this? Just pretend not to seeing it. So this is the column J of the Jacobian for body I, right? And you see how this goes. It's pretty easy to say. Jij, so the ij column is, you take the xj and you transform it with hij. Just remember that one. So the body I column joint j goes like this. Well, I'm saying this because we can, of course, so you haven't seen this? So we can, of course, plug this, or let's say summarize this for all the joints, for all the bodies. What I'm saying is that, for example, this is the, yeah, maybe this is also, yeah. So I left it in there, but it's not handy. What happens actually if you look at the first joint? That's why I'm going back. What's happened if you looked at the first joint? The first body, first joint. So body number one only depends, of course, let's say this is the ground, and that's body one, right? Of course, the motion of body one only depends on the first joint number one, right? So then there's only one column, which is the first one. And what happens then? You would have H11. So you transform from 1 to 1, which is the identity, right? So essentially H11 is X1. Good. What about the Jacobian of the second body? The second body, so we have to, so I is 2, second body, and then J goes from 1 to 2. What about, and this is generally true, JII is always, because then you have II, which is the identity, JII is always XI. So also J22 is, of course, X2. What about the first column in the Jacobian of the second joint? Well, sorry. What about the second column? No, I'm sorry. What about the first column in the Jacobian of body 2. So the first column of the Jacobian of body 2. So we have 2, 1. Yeah, it's just at 1, 2, right? So, and so this is apparently, there is a bit of a structure behind it. Yes, and that goes here. So J1 is the identity. I mean, we said J1 is X1, okay? So if you plug them all in this big kind of matrix, what I'm doing here, this is the Jacobian of body 1, and so on, up to body n. So we have essentially, this is a 6. So what's the dimension of the Jacobian of the body I? It's 6, because we have a 6 vector, times the number of joints. So it's a 6n matrix, right? So, and that is what? This is a 6n times n, right? So it's a big fat, tall and fat, it's everything, matrix, okay? So, and now J1 is, of course, we said x11. J2, which is the next one, is, as we said, it's x2. That one, this is the second column. And the first column is at h21 x1, because if you multiply this with h and so on. And you see that there is this kind of a triangular structure here, right? And that's that's also an important important relation, because this is a factorization of the Jacobian. And this big matrix is called the system Jacobian, in a sense that you have, for all the bodies, you have the individual Jacobians in there. And if you multiply this kind of system Jacobian, there's no index because it applies to the whole system, to get the complete kinematic chain. If you multiply this with Q dot, then exactly, multiply this with Q dot, what you get out is the system twist, in a sense that you have the twist of all the bodies in it. And that is very handy. And now remember, if you want to implement this is super easy, because this is constant vectors. And this is, anyway, you have to do this. This is just this 6-6 matrix, and you get these H matrices, you get them out of the exponential, product exponential. And that's it. So there is a purely geometric way of doing this. No DH parameters, nothing. And as I was saying, we have a package if you want to have it. So it's all there. And there are other packages that, of course, do the same job. Yep. So, makes sense? Good. Yes, that is probably maybe the same, just summarized. I don't know. Yeah, so as I was saying, I mean, this kind of splitting here, you have these two matrices that in the end make the Jacobian. That's, it's a, oh goodness, it's a factorization of the system Jacobian, right? So now your Jacobian is A times X. If A is this adjoint triangular transformation matrix, and X is just the diagonal matrix that I had shown here. This is the thing here. Okay? Yeah, that's it. So essentially, you have everything you need on hand to actually implement the velocity kinematics. Okay, good. There we go. There we go. Yeah, there is much more to say. I'm not sure if you want to. In many cases, well, in some instances, you need the invert this A. So we have been saying A has this triangular structure, which is of course true. What's the dimension of A? Of this big A matrix? So each of these adjoint is a 6-6 matrix, right? So we have 6n times 6n. So at least it is a square matrix. So that makes, at least we can hope to be able to invert it. And it's actually invertible. It's well conditioned, by the way. And the inverse, you can write the inverse as a power series. That might not be interesting at the moment for you, but it's interesting for later on. You know, if you, for example, look at this matrix here. So what this matrix does, it's, or how it's structured, at the diagonal terms, you have zeros. And then the lower diagonal is, you know, having all these relative transformations, because here we have the transformation from 1 to 2, from 2 to 3, and so on, from n minus 1 to n. Okay? if you have time and interest, just try to take powers of this, right? If you take this to this, okay, if you multiply the d, and we call it d for some reason, if you multiply d with itself, what do you get? Not easy to see, right? Does anyone see what happens? When you multiply this kind of matrices, when you have the 0 on the diagonal and just one lower diagonal left, what's happened actually is that it all shifts one further down. And you get, here you get H31, no, one further, H31, then you get here H42 and so on for the first power. The second power, it goes like this. And then, and immediately, of course, you can do this n times, and that was it, because then nothing is left. Then it's the zero matrix. And this is why it's called a nilpotent matrix. Because a matrix that after some powers becomes the zero matrix is called nilpotent. And n is just the power up to this. Okay, and because of this, just long story short, because of this, so the first message is I can take powers of this, and apparently it's A. So just look at this one. A is equal to the the sum of the powers from 0 to n of that matrix, which means that is actually the same as this. Because if you remember your math course, what was the Taylor expansion of 1 over 1 minus x? What I'm referring to is, maybe you remember, maybe not. What you have a function which is 1 minus x. What's the Taylor expansion? Do you see? Exactly. You're an expert. So 1 plus x squared and so on. It's too much for me. Okay. And more generally, if this x is an operator or a matrix even, the same applies, right? So this is the same, like, I mean, this is 1 minus x to the power of minus 1, right? So, and this is called the von Neumann series. Anyway, so, and apparently we have this here, because this is essentially the same. With the condition that, I mean, by chance, after power n, I mean, n plus 1 is 0. But nothing stops you from saying this goes to infinity, because you can go to infinity and nothing happens. Okay, having concluded this, we know that now that actually A is the inverse of I minus D. And that's it. Because now I know that the inverse of A is I minus D, right? And that's quite a handy solution. It's quite useful. In many, so this is later on, maybe, if you manage, for dynamics and stuff, this is going to be an interesting, useful relation. There is some, maybe stop here for a minute. You talked about forward kinematics. Do you know inverse kinematics? What's the inverse kinematic problem? Yes, correct. You're given the pose, like here. You're given the pose, and you would like to know the q. That's the geometric inverse kinematics problem. What about the velocity inverse kinematic problem? That's the inverse of the forward kinematic problem, right? So the forward kinematic problem was that you're given the joint rates, the joint velocities, q dot, and you would like to know the velocity at the twist at the end. Now the opposite is the inverse, right? So you're given the twist at the end effector, and you would like to know q dot. How do you do this normally? Let's say you have a robot. How do you do this? If you have so you buy your 6 degree of freedom robot. How do you do this? How do you solve the inverse kinematics, velocity inverse kinematics problem? Yes, correct. So it would be like this. So V, I'll just skip the indices, is J times Q dot. And you say that the inverse is, I would like to know the Q dot for given V. And you say Q dot is equal to J inverse times V, right? What are the conditions for that to make sense? Yes, J should be a square matrix. Let's say n times n. Anything else? Yes, non-singular. Correct. So the determinant of J should be non-zero. Okay. So when does it happen to have a zero determinant, for example? And you say singular, right? Because if it is zero, then we call it the singularity. So singularity means that the rank of J, actually J of Q maybe. So J of Q is less than N, okay? In our case. Good. And then if this is the case, then Q is a singularity. Okay, this is how it's, I mean, very simply speaking. Okay. And when does it happen to have a singular Jacobian? Or does it not happen? Or maybe I go here? No. When does it happen? I'm looking for a nice picture while you are thinking about the answer. No, that's not a nice picture. Maybe I have a... Yeah, maybe you go to the first one. Okay. So when does it happen?
Maybe when we have less number of equations than numbers.
Mm-hmm. Oh, yeah. I hope you can see it. It's a bit blurry. Less number, yeah, okay. But I talk about a robot. So let's say this is our forward kinematic Jacobian. So we have a 6 degree of freedom robot. So we have a 6 times 6 matrix. And now, I mean, usually this should have a full rank, 6. When does it happen to have a lower rank? Yeah, I know, but physically. Okay, what I'm saying is, so what you're saying is that, so we have the forward kinematic, these are all 6 degrees of freedom robots, right? What pose is it? I mean, what kind of situation is it that we get a rank deficient Jacobian? Maybe it's not that easy. What does the Jacobian do? It gives you the end-effector twist in terms of the joint velocities, okay? Now, if you look at that robot, for example, right? So when I talk about the joint velocity, the end-effector twist, so I'm sitting here and I'm measuring the twist that I can generate. And look, maybe, so there's an omega. Okay, let alone omega. What about the linear velocity? So the linear velocity, yeah, I don't know. It's just a vector in space. Okay. Is there, what happens, for example, if this is straight upright? So like this thing is as here, for example. Let's say that we are looking at this this configuration. So they're all Revelet joints. So what kind of linear velocity can you generate? So I'm asking about the linear velocity of the end effector. So you can generate, I mean, you can turn, I don't know, this one, for example, you can have a linear velocity in this direction. You can rotate about the verticals, this one and so on, and you will have a, no, what is that? No, you will have no linear velocity. But you, yes. So you cannot generate in this direction linear velocity, and you cannot generate in this direction, right? So you're actually losing 2 degrees of freedom of the end effector. Okay, and this is actually when, so, and this is the reason, because when I say you lose 2, maybe loosely speaking, you're losing 2 degrees of freedom of the end effector means that you are not instantaneously able to generate certain directions of velocity. And this has to do, as you say, I mean, the Jacobian becomes singular. And when I say losing instantaneous degrees of freedom means that some of the some of the columns of the Jacobian become linearly independent, linear dependent, right? Which is generally, from a linear algebra point of view, the condition for having a Jacobian that's singular, okay? Now, there's a whole business, I mean, there's a big research going on singularities and how to avoid it and how to, you know, analyze them. You could use a different thing because you are going to be, I don't know, you will be an engineer one point in life. So this is, of course, bad, right? It's not good to have singularities. But you could think the other way around. Is it maybe beneficial to have singularities? Are you using singularities? You say, no. Oh, okay. Are you sure?
For calculating the limits I'm using. Because at this point it should not be.
Yes. Okay. This is you as someone that does a PhD. But if you're not just say that the 2 hours per day that you're not doing a PhD, are you using singularities? Maybe you do. Okay, what I'm saying, what I'm asking is, or what I'm referring to is, there's a duality between velocities and wrenches. I mean, force, torques, and angular velocity and linear velocity. Because when you can not generate a velocity, it always implies that you can withstand a force and a torque without any motion. Okay, what I'm saying is, imagine that you are pushing vertically down. Just apply force at the end effector. How much joint torque do you need? I mean, ideally, of course, if everything is perfect. 0. Exactly. So you can have an infinite, an arbitrary magnitude of or intensity of force, but you don't need any joint torques. Okay. And this is because the forces, right, let's say wrenches, they are transforming. So now this is from joint velocities to end effector velocities. Okay. What about the inverse? Not the inverse. What about the dual relation from? Okay, what I'm saying is I would like to call this W, and W is the what is it then? The moment and the force at the end effector. Okay. So, and how do you get the generalized torques? They call it Q normally, right? I'm not sure if you're familiar with this. So this is the joint coordinates. The Q is the joint coordinates, and the Q dot is joint velocities. And the capital Q are just the torques. So this is like Q1 up to Qn. And these are the joint torques. Maybe you call it tau. Sometimes you call it, okay, maybe better call it tau. Okay, so let's call this tau. Okay, so you have the joint torque 1 to n. Okay, there we go. Okay, so what's the relation? How do you get from here to here? So here we went from joint space to end effector space. How do you get from end effector space, the wrenches, to the joint space, the torques? Oh, there's no dynamics. We have no idea about dynamics. It's all kinematics. It's all kinetostatics, so to say. Well, that is actually not difficult to see if you see it. So let's. So what do you know about? I don't know. What do you know? What about the power? So there's many times when you want to have when you would like to have to derive relations, kinematic, kinetostatic, it's good to look at invariants. And an invariant in our case is the power. Because the power at the input should be the power at the output. Because we are not losing energy here, right? So, okay, what's the power at the, I don't know, at the end effector? So what is power? Power is, so generally, the power is defined as, yeah, okay. So essentially it is force times velocity, right? So in our case, it's the twist times the wrench. So it's like the moment times the omega plus the force times the linear velocity. This is what you get when you compute this. Okay, wonderful. And that's the power, okay? Now I can, of course, plug in what I know. I know that this is J times Q dot, okay? So V is this, all right? All right. And as I was saying, I mean, this should be an invariant. So you could measure it at the end effector, which is here, but you can also measure it at the input, at the joint space. It should be the same. If it is the same, then what we call tau should be here, because then whatever we multiply with Q dot should be the corresponding joint torques. So that must be tau transposed Q dot, right? And that means actually that you have, because this is this, oops, this is this. That means that tau is equal to this one, to J transposed W. So you see exactly that now the transformation of the wrenches to tau is just via the transpose of T of J. So you have this duality. When you have a velocity transformed with a Jacobian from joint space to end effector space, then the transformation from the wrenches to the moment and forces is via the transpose of J to the joint torques. Okay, wonderful. Why did we talk about it? Because I was asking if you're using singularities. And exactly this is what happens, because you can see that if this J transpose, this J is singular, we set at least, this is because some of the columns are dependent. Okay, that means that some of the rows of J transpose are dependent. Okay, which means what? Which means that some of the taus are dependent, and you can then conclude if they are dependent, then you can they kind of compensate each other, and that's the reason why you get actually you are able to perform or to apply a force in this case. There are different situations, but in this case you have a force, but you don't need, because this is in the kernel of in the null space of the Jacobian, right? And you don't need this. You don't need the torques to compensate this. Okay, so again, my answer is, my claim is you are using singularities, because what happens if you are lifting a heavy object? How do you lift a heavy object? Do you do it like this, or you do it like this? Well, it depends how strong you are, but mostly you do like this, right? Why? Because your arm is stretched, and you do exactly the same, because you apply a force here, but you don't need a joint torque. I mean, a little bit because you bend it, but that's it. You can do it like this, but then you feel that you need joint torques, right? You do like this because you are in the singularity and you use this. I guess you use it. Sometimes you use it. Okay, wonderful. There we go. So we have to kill 1 hour, I guess. Huh? What's this? Oh, someone is calling for someone. Okay, this was the lecture from the first day. Yeah, okay, so there we are. Yeah, so that was the inverse. So, okay, we started actually with the inverse kinematics. And you said, and we said, the inverse kinematics is just taking Jacobian inverse in case we are in a regular configuration, not in a singular configuration. By the way, almost all configurations are regular. So the other way saying singularities are unlikely. So whenever you pick randomly a configuration is regular, it's not singular. But still the singularities are there and you will meet them. So taking the inverse gives you the inverse kinematic solution. But there is a different kind of version of an inverse kinematic solution problem. Let's call this a kind of a global velocity inverse kinematic problem. When I say global, what you did here is just asking, okay, I have the end effector twist, and I'm asking for the joint torques. Okay. What if I'm given actually the twists of all the bodies? Of all the bodies of all the links in the system. For example, I'm giving, the velocity of, I don't know where it's here, this link, I mean, all the links, 6 links. And I would like to know the joint velocity. Why is this an interesting problem? Who's working with motion capture system? Mocap? Like optical? No? Because this is what you do. Okay, this is what you do when you work in biomechanics, for example, right? So what you do, you have these markers placed on the bodies, on the on your body, on the, so to say, many bodies, because our body is split into different links, parts. So you have these you have these markers, reflective markers, right? And then you have a mocap system, like a couple of cameras, 3D cameras, and they capture the marker positions, and then the problem starts, because now you have, for each of the segments of the human body parts, you have given a position, for example. Okay. And now the question is, what's the pose of the whole body? And you solve this by looking at the velocity problem. In other words, saying, okay, now you are given the velocity of each of the body parts, and I would like the velocity of my body, I mean, of the whole human body model. That's the way it goes. Which means that I need the velocity of the joints. I mean, the technical joints that I use to model my human body model. You have seen in the first day, I have shown you this kind of model, human body model. Okay, how do you do this? Okay, this is where it comes from. So given twists of each of the individual segments, and I would like to know the joint velocities. And that's the, maybe call it the global inverse kinematic problem. And what we are given is, and this is why we now have this system Jacobian, because what was this system Jacobian and system velocity doing? So the system velocity was where we have all the twists of all the bodies in it, right? And of course, we had then the system Jacobian, and everything is fine. That's it. So then we said the Jacobian, we can factorize it in a sense that we have a times x, okay? And now comes the interesting thing, that we know that the inverse of a is this, I minus d, and d was this funny matrix. And of course, then the inverse of a is I minus d. So if I multiply this from the left with the inverse of a, I get inverse a, which is equal to this one, is equal to x times q dot, okay? And then we can so then we have what? We have an overdetermined system. Do we? We have an overdetermined system. Yeah, because we have, how many equations do we have here? 6n, right? Because we have, remember this v, the big system twist, that was maybe the other way, this one. This was the system twist was comprising all the twists of the n bodies. So 1 to n. So it's 6 times n. Or n times 6, whatever. And that's it. So we have an 6n equation for n unknowns, because the q's, I mean the q dot, they have n components, and I would like to compute the n components from the 6n equations. So, and then it's always the same. You multiply this from the left with this x transposed. So x, what is x? X has the dimension, what's the dimension of x? X was this one here. Actually, this is x. How many? So each of them is a 6 vector. Yes, so it is. We have n of these 6 vectors, so we have 6n, and then of course each is a vector, so we have n. So it is 6n times n. Okay, that's that matrix that goes in here, which makes sense because this is a 6n times 6n. This is a 6n times n. What comes out is, of course, a 6n times n matrix that we're looking for. Okay, good. Yes, and that's okay. So the transpose, okay, we said this is 6n times n. The transposed is, of course, an n times 6n. And all this together makes, of course, a what? An n, what? Yes, an n vector. That's it. No, what? No. Okay, so this is an n cross n matrix. Now I have it, and that's an n cross 6 matrix. N cross 6 n matrix. Because we have 6 n components here, that gives you n equations at the end. And the important point is that this x transpose x is an n times n matrix, the whole thing. And it's invertible because the x's are just constant vectors. If it is invertible, I can multiply, left multiply with the inverse of this matrix, and I get q dot equal to this. Okay. Okay, and maybe you have seen this kind of expression sometimes. Okay, what we get is the final version is like this, so q dot is this. Have you seen this kind of equation? Or this kind of relation? How do you do, like, again, the inverse kinematics. What if J is not square? The pseudo-inverse, correct. So then you take the pseudo-inverse. And taking the pseudo-inverse, we have to have a different symbol, right? So we say then Q dot is equal to J times V, but not the inverse, but the pseudo-inverse. And we use plus. Many people use plus. Sometimes they use a little cross or something. Yes. And how do you compute the pseudo-inverse? Exactly. It depends on the size of the matrix. And if the matrix is, what is it then? It could be a tall matrix or a fat matrix. So if it is, in our case, well, this is not a good example because normally here, when you have a redundant system, it's actually a fat matrix. In our case, it's a tall matrix because our Jacobian is a 6n times n matrix. Now the pseudo-inverse, I mean, we can show this, but maybe not time for that. The pseudo-inverse of a fat matrix, of a tall matrix, sorry, like here, is this. So this is the pseudo-inverse of a matrix that has more rows than columns. What does it mean to be a pseudo-inverse? It is also called the left inverse. Why? I mean, what does it mean to be a pseudo-inverse? What does it mean to be an inverse? So when you have a matrix and you say the matrix is an inverse of another matrix. So when you say you have a matrix A, for example, right? What does it mean to have to be the inverse of a matrix A? It's simply if you multiply it with A, then you get the identity, right? And of course, it's the same if you multiply it from the right and from the left, like here, okay? Not difficult. So now you have a matrix A, and the matrix A is, let's say, an m times n matrix with m, what is it now? With m bigger or bigger equal than n. Okay? So this inverse doesn't exist because you can't take an inverse of a non-square matrix. But we said, because this is our case, what we said is that we have a matrix called A plus, and we define it like this. We say this is A transposed A, inverse A transposed. I mean, first of all, we have to check that this makes sense. So A transposed A has dimension n times n, right? So which is the smaller dimension of the A. So this is invertible because it's an invertible. Again, m is bigger than n is smaller than n. What you get out is an n times n matrix. And if this, of course, all is full rank, then this is invertible. So fine. And then this is an n times n matrix. And A transposed is again, it's an n times m matrix. What? Yeah, it's an n times m matrix. So what comes out here is, of course, it's an n times m matrix. So at least somehow it fits in a sense that you can ask now, what happens if I multiply this matrix with A? As we did for the inverse, right? But you have to be careful because the standard inverse, it doesn't make a difference if you multiply from left or from the right. But that's not the case here because the pseudo-inverse depends on whether it's a fat or a tall matrix. And that's why they call this, for example, the left inverse. Yes, the left inverse. No, yeah, the left inverse. Why? Because if you multiply A with A plus, what you get, you see here immediately, is A transposed A inverse times A transposed. And now comes, yes, I said the left inverse, right? So, and it's the left inverse, A plus A. And now comes A, okay? And that, of course, is exactly, this is the inverse of that thing here. And what you get, of course, is the identity. Of course, it's the identity matrix of dimension n times n, okay? So, and that's why it's called the left inverse, because if you multiply A from the left with this A plus, it gives you the n times n inverse. And of course, there's a right inverse, which you don't need here. Okay, good. Yeah, so, and that's actually the solution. So this is the left inverse. And if you look at the structure of X, remember that X had a certain structure because our X was exactly this, right? So we had this. Now, what happens if you take X transpose X? If you take X transpose X, essentially you get a diagonal matrix where you have X1 transpose X1. Then here you have X2 transpose X, and so on, right? So that's number one. And then what we said, we have to take so this was this guy. They take the inverse. But the inverse is just the diagonal matrix with, well, the inverse of a diagonal matrix is the diagonal matrix with the components, 1 over the components, right? So this is this. So essentially this is this. Times. Yeah, okay, this is what I'm saying here. Yeah, this is this. And then you have to multiply with X dot, X transposed. And there we go. And that's it. Yeah, and in the end, if you multiply this out with this D, particular form of D, then you get a closed form for the component. Because what is interesting, this, of course, you can compute it, but of course you have big matrices. You can do it, but maybe it's nice to have a closed form for each of the components. And this is the one that you get. So the QI dot, the QI, the ith component of or let's say the velocity of joint number I, this is what it is. The velocity of joint number I, the time derivative of the angle I, for example, is exactly this. So you just take the screw coordinate of joint I and then the twist of the body I, and then you do this. At the closed form solution, that gives you the joint velocities of your model when you are given the velocities of the individual links. And one application is, for example, when you have mocap system, motion capture system, 3D motion capture system, where this comes from an optical motion capture system. Or if you are given, for example, IMUs, right? So you have inertia measurement units, and you might be able to actually take the IMU measurements to get the velocity of the individual links of the system. Okay, what else? Yeah, and then maybe this is the last thing. We already talked about it. The forward kinematic, the forward velocity kinematics problem of of a robotic manipulator in a sense. You know, we talked about this many times already. Given the joint velocity, would like to have the end effector velocity, and then the only thing is, oh, sorry, this should be going away. Then in the end, so normally this is called n or just nothing. Then this all goes up to n, so we have all the n columns in there, and these are just the instantaneous screw coordinates of the individual joints, and that's it. Yeah, and this is what you find in many textbooks as the forward kinematic, the geometric forward kinematic Jacobian of a robotic arm. Okay, there we are. There we are. Do you have any kind of questions so far? I know it's a lot to take in. I hope it somehow resonates what you knew before, maybe, hopefully. So we have about, what is it then? Half an hour left, I guess. So we could possibly have a bit, look a bit into the computations again, because it doesn't make sense really to start a completely new topic. But anyway, we can look at the computations for the Jacobians now, because what you did, we looked into how to use the exponential mapping to get the forward kinematics of the kinematic chain, and now we should actually do the same with the velocities. Yeah, so and let's say that we would like to have the body fixed Jacobian, and maybe recall the definition of the body fixed Jacobian, which was here. Okay, so this is the body fixed Jacobian that we had introduced, and essentially what we said, we take the body fixed joint coordinates, I mean the body fixed screw coordinates of joint J, to get the column J of the Jacobian of body I. Okay, so body I Jacobian, column J. I have to take the screw coordinate of the joint J, and then I have to transform it according to this homogeneous transformation matrix. Let's see how this works, how this goes in practice. I mean in implementation. The easy thing is, oh sorry, what is this? X1. Oh yeah, we have to define it first. X1. Yep. So X1, there we go. So the screw coordinates in our case that we had, okay, so we are looking at the example again of the two-link manipulator, right? So, well, here we have it in the slides anyway. So the SpaceX frame was located here. That was X, Y, and Z. And so what are these screw coordinates of joint number 1? I think we had it before, we did it already. So the body fixed screw coordinates of body 1, of joint 1, sorry. So, no good. So this way. Maybe I go to the picture, because we had a picture somewhere. Where did we have it? I don't know. I think we had it somewhere. No, it was the other slide. Oh yeah, I guess it was, yeah. So, no. Yes, yeah. Okay. The body fixed screw coordinates of joint 1. That means the screw coordinates of the joint expressed in F1. So what is it then? We need the unit vector along the joint axis. Again, this is the 0, 0, 1, because we are along the z-axis. It is the z-axis here. Then we have to measure from here to here and take the cross products, which means that we need to take, first of all, the the cross product, and the cross product of what? The vector. So you have to switch back and forth. Sorry. So the vector. Maybe I should write it down. So the vector that I'm talking about is the vector. We called it x 1 1, and this is a little x because this is the vector, right? So what is it then? It's the vector that goes from here to here. And let's say we go from here to here because this displacement makes no difference. Which is the length is L1, so it's L1 half, I guess. Okay. L1 half in minus x direction, so it's minus L1 half 0 0. Okay, that's the x1. So the E1 in the one frame is of course 0 0 1, and the cross product. No, the other way around. X1, oh goodness, E1 is, who can compute this? So, so, But let's, I mean, okay, yeah, you want to do it with the tilde, with the scusiometric matrix. I mean, what just about the cross product? I mean, maybe you can just do it without the tilde matrix. So what is this vector? Oh, I'm sorry. Yeah, this vector cross this vector. Cross product. Yes, there's a 0 here, there's a 0 here. And this is, what is it then? This is the x, z, which gives minus y, is L1 half. Okay? And that should be the cross product. So in the end, the big vector x1 is, of course, the E1, which is 0 0 1, and then comes this in here. Okay? And let's see if this is correct. Let's see if this is correct. I mean, at least our system gives the same. Yes, it does, because it's here, right? So this is essentially 0 0 1. Then we have 0 L1 half and 0. Exactly L1 half. Okay. Okay, and this is the screw coordinates, the body fixed screw coordinate of the joint 1 expressed in F1. Now what I need for the second joint is the body fixed screw coordinate, x, capital X, 2, of that joint in this frame, relative to this frame. And it's essentially the same, right? Because what you're doing, you're measuring the unit vector in this axis, in this frame, and you measure the distance from the coordinate, from the frame to the axis. Of course, now it's not L1, it's L2 half, okay? But the rest is the same. So you should get the same, just replacing L1 with L2. And there we go. So now we have the body fixed screw coordinates. And now what I can do is I can, of course, go to the Jacobian. So the Jacobian is exactly, so, and the first, this is what we had in the definition of the Jacobian. Somewhere. The first one, x1 of body 1 is just, I'm sorry, J1 of body 1 is just, this is the identity again, it's just x1. Okay, this is what I had here. So the first the first column of the Jacobian is exactly x1. Body 2, the, how does it go? This one. The second body, the first column. So the first column of the Jacobian of the second body tells you the contribution of the first joint to the velocity of the second body. Okay. Yeah, and it goes like this. I mean, this is what we had here. You just read it off, the formula. What you have to do, you have to take Hij. Now, in our case, Hij is what? So we're talking about body 2 and joint 1. Okay? So body 2, joint 1. In body 2, joint 1, in this formula, I need H21. Okay? And H21 is what? It's the homogeneous transformation from frame 1 to frame 2. How do you get this? By combining what you know, because you know H1 and H2. So you go from you go from 1 to the ground with H01. And then you go backward from the ground to body 2 with the inverse of that one. And that's it. So, and this one we know, because this is what we get from the product exponentials. This is what we did before. So we just have to compute the inverse of this times this. And then you have to plug it into this adjoint. And of course we have this implemented. We have a code for this. And what comes out is exactly this. And you really do like this. So we take the inverse of H2 times H1, as I was saying here. Take it into this SE3 AD matrix. Essentially, this function plugs the rotation matrix and the position vector of this homogeneous transformation matrix into this adjoint matrix. Then we multiply it with x1, and then we get the first column of the Jacobian of the second body. Okay? And there we go. And for the second column of the Jacobian of the body 2, it's again just x2, according to our formula, right? Because in our formula, we have 2, 2, which is the identity, and this is just x2. And there we go. That's actually the end. So then we have the, what is it then? The second column. And then all together, this is column 1, column 2, and this is the Jacobian. So now you multiply this with Q1 dot and Q2 dot, and you get out the twist of the body 2. And that's it. Yeah. Yeah, okay. And that's, yeah, we can do a bit of checks and stuff. Yeah, okay. I guess people are leaving now, so I guess we're a bit over time, but we started a bit late, so. Yep. So this was the example I wanted to finish. I'm not sure if we should maybe have a bit of time for questions or. Yeah, but we still have. I know, but I'm not. I would better ask people to have questions, because it's a lot already, and it's better to see if you have other. Yeah. Maybe I go through another example, just for entertaining you. Do you know the Panda, this Panda Emica robot? No? Panda Emica. Hey, what's going on? So essentially, it's a standard. No, maybe not standard, but it's a 7 degree of freedom robot. Takes a bit of time. Yeah, like this. So it's a 7 degree of freedom robot. It's a small, well, there are bigger and smaller ones, but essentially it's one of these what they call a collaborative robot for human robot interaction. So in some sense they say it's kind of a safe robot in a sense that it's lightweight and it's compliant, and also it has force torque sensors in the joints, in a sense that if you are somehow touching it or colliding, then it's supposed to stop, and somehow it's safe. Anyway, so it's a 7 degree of freedom robot, and in the data sheet of the company you find all the geometry. So we have 7 degrees of freedom. This is 1, 2, 3, 4, 5, 6. No, what's 6, 7? I don't know. Must be 7 at least. Anyway, so 7 axes, and yeah, it's the reach is 0.8 meter. It's 80 kilogram. Yeah, it's a bit of a bigger one. Anyway, and so what we did is, of course, in our MATLAB software, we have all implemented that stuff, right? So what you do, and yesterday I referred at the very beginning, I referred to data structures in a sense that how would you implement a code for kinematics and dynamics and stuff like this, and now we have like a data structure that is called parameter, right? So and the parameters are, it depends what you know. I mean, if you know already the screw coordinates, you can plug them in, right? And we have them here, for example. So we have, for the 7 joints, we have the spatial screw coordinates implemented, and this comes from what you read off the data sheet. And then, of course, we have the reference configurations with respect to the inertia frame. So this is actually. I should maybe dig out a picture, because no, that's the universe. Next one. No. No. Yeah, there we go. So this is the panda that we looked at. So, and you see exactly you see the dimensioning, you see the joints. This is joint number 1 and 2. I mean, this is joint number 1, but joint number 2 goes like this, number, and so on. So, and in this reference configuration, you can read off actually the poses of the frames. That means of the bodies. So there is it's a bit of strange, not the best picture, but anyway. So this, I don't know which one is what. Yeah, this is number 2. Like the frame of body 2 is the orange one, and the body 1 is the red one, and so on and so on. And from here you get what we need, and from there you get the data that we have in here. Yeah, the absolute pose in the reference configuration of the body 1 to 7. Then we can also conclude the relative body inter-body reference configuration, because this is the reference. Maybe I start here. This is body 7 relative to body 6, body 6 relative to 5, and so on. And actually, this one is the same, because this is the relative configuration of body 1 with respect to its predecessor is essentially the same as the absolute, because the predecessor is the space fixed reference frame. Then we have the x coordinates, right? And you see what we do here. We use this transformation with the adjoint, because when you have the screw coordinates in one frame, you just take the corresponding adjoint and you get in the other frame. And what we're using here is like we first had the screw coordinates, the y's, in the spatial frame, and then we transform it to get the ones in the body fixed frame. And then in the end, we have everything that we need. Yeah. Okay. So That's the parameter setup. And then we can go further, and then what? Okay. Set dynamics parameters. Okay. And then we have kinematics dynamics. And then we can do a lot of things with this. Maybe the Jacobian. Yeah, and then you can, for this robot, you can actually just, it's a very simple kind of one loop, right? Because what you do exactly as I was saying. You take, by the way, C is H. We use C in this case, but this is essentially the H. So we have the inverse of n of Hn times Hi. Because what we are interested in is the forward kinematics. And the forward kinematics is always going to the last link, right? So this is the Jacobian of body n, the last one. So, and it's the same formula, the same as we did before. Now the 2 becomes the n, right? And we have then Hn inverse times Hi, and then times Xi, and then what we get out is the Jacobian, the column of Jacobian, the column I of the Jacobian of body n. It's getting late now. And that's it. So, and then we have the Jacobian. So it's pretty simple to do. And what else do we need? Yeah, that's it. We can do a lot of things here. And the same is with the computation of poses. You can compute the relative pose of body I with respect to its predecessor. And as we have been saying, this is just bi times the exponential of xi times qi. And there we go. And the absolute, remember, this is what we said. That's actually the relative configuration of I minus 1i is bi times x of capital X I qi. Okay, that's what we said. This is relative from I relative to I minus 1. And of course, we get hi, if you want to say 0i, by saying this is hi minus 1 times hi minus 1i, right? So I was referring to this one. So this is h0i. This is the pose of the predecessor of I. So I minus 1 predecessor, and then multiplied with the relative configuration of I minus 1. So you get hi or h0i. And that's what we do here. And again, this is a simple for loop, and that's it, right? So you have it all there in some sort of a simple expression. Yeah, and then what else I can do? You can do the inverse kinematics. And the inverse kinematic, yeah, okay, this is something maybe for the next lecture, because that needs a bit of explanation. Do you know how to solve the inverse? So we kind of discussed the velocity inverse kinematics, right? So you take the inverse of the Jacobian. That's easy. You do it and that's it. But how do you solve the position inverse kinematic problem? Because you have to solve a nonlinear equation system. And what you do some Newton-Raphson iteration scheme. So you use the Jacobian to compute little increments, small increments. And then you kind of converge to the solution for the nonlinear system. Yeah, and this is what we do here. Maybe this is too much for now. So we have seen the code, we have seen the equations. You get the slides. If you have questions.
Any questions? Or any requests?
Or any request, yeah. Or any suggestions, or any. What I'm also interested, maybe for you to get something out of the course, more than listening. If you have a problem that you would like to discuss with us, with the group or so, Yeah.
understanding or not understanding,
Yeah.
which part is full of like a bounce from your head.
Or in your research, somewhere you would like to help, to get help. Oh, I don't know what.
I think these two are the PhD student. These two are the MTech student, and the last one is PKM.
Mm-hmm.
So these are our permanent, you can say,
Participants, yeah.
Yes.
Yeah, somehow forced to be here, right? Yeah. No, I guess you're working on this stuff more or less, and maybe.
Can you suggest, can you just share your work, what type of work you are doing?
Yeah, that would be
That
nice.
would be at least
Yeah.
he will listen about your work, what kind of work you are doing, and how this course will help you in this plan, in that work. How it can help. So can you discuss one by one, like you are doing in underwater robotics?
I am working in underwater vehicle manipulator system. In that, my objective is to perform a pick and place operation
Underwater.
underwater. The main objective of my is I have to mathematically model it,
Mm-hmm.
considering the coupling effect of manipulator with respect to the underwater door.
All right.
And then in that objective, initially I'm working with this DH parameter and conventional methods, but my guide has suggested me to switch it to skew theory. Therefore, I am taking this course.
That makes sense, yeah. Mm.
Means what kind of advantage is there in skew metrics?
Computation in level of computation, as told.
Even we can ask to professor that one. Means,
Yeah.
what kind of advantages
Mm.
in skew symmetric metrics as compared to the conventional DH parameters?
We had it in a lecture already, the summary, but I as I was saying, I mean, the advantage is hopefully clear. The data, essentially, it's the way you model it in a very compact form. You don't have all these intermediate DH matrices and so on. This is one thing, and maybe the most important point is the parameterization, because you have only vectors that get into the equations, and the vectors are easily found from your model, instead of having all these tricky DH parameters and so on. That is certainly the most important point. And you see this compact kinematic formulation with this big matrix. It actually is the same for the dynamics. So it is transferred to the dynamics, and the dynamic equations are very simple actually in the end, because normally dynamics is not that easy. But it's interesting. So how do you model the fluid structure interaction?
Fluid structure means that there we have to calculate hydrodynamic forces also.
Okay, so added mass and stuff like this.
It's added mass.
Yeah.
Without it, we cannot perfectly model.
No.
Still, I am facing problem in coupling the manipulator as well as underwater. So in this there is also EDM manipulator also. Hence the same concept. If I got it from here, then I can apply it in that underwater.
Yeah, but the Reynolds number is a bit different.
But still means mathematics will be same only. Means some additional parameters will come in underwater, like added mass, curvature, added forces, everything also.
Cool.
We will be discussing a little bit about couple dynamics also. And it will be helpful for me.
Well, we have to see how to get to what we planned, and then let's see. Yeah. Let's first go to the dynamics, and let's hope we manage this by Friday.
Yes.
Yeah. Thank you.
Sunny, yours? How do you want to any help from this kind of research?
My work is related to the design and development of a contact-based functional space and to do the analysis of water space and trajectory analysis. Right now, I am designing the compact mechanism so that we can remove the rigid joints. According to that, we will get the frictionless motions.
I think we can visit our lab.
Yes, this would be nice. This would be
We
really.
can go.
Yes.
Is there any key? And also you ask Rishi to join.
Yeah, would be good. Yeah.
And you?
Sir,
Why you came here?
I am a BTech student of second year. So recently I have started working on lower limb applications on the lower limbs. So currently I am not gone very deeper, but I am studying about
So like an exoskeleton, like an orthosis. Yeah. Okay. Active or passive?
what
Active or passive? I mean, is it a passive mechanical system or is it an active system? You have motors in it?
yes,
Okay.
Thank you. And he is also one of my PhD, just recently joined.
I know.
I have joined the PhD under Julian. So currently I am working in the design and development of lower limb rehabilitation program. So it's supposed to be quite helpful for me because I am starting this in robotics and the dynamic part and the dynamic part.
At least you can use these methods
Yeah.
to model the mathematical modeling of your system. That would be helpful.
That's true. That's true. Yeah. That's true.
So it would be also one kind of contribution from your side that whatever you have learned, that you have implemented in some kind of real problem. Try to understand it, grab it, use this whole week, and then use little bit to in your systems.
Wonderful. So you have similarities, I guess, right?
He is a PhD student, he is BTech.
So you
Here can the
transfer the work to him. Very good.
Sir, right now I'm focusing on this 3D printer, Scala 3D printer. Like I have found one
Okay.
interesting, with modern 3D printer. So it's basically polar 3D printer. So what? So I found this one difficulty like maintaining the speed around the base area, so you can print around the base area. So I think this can help. It's helpful.
So 3D printing of what?
3D printing of right now I'm focusing on plastic only.
Plastic. Like what's?
Like other 3D printer can make the build plate bigger, larger. So I think it's an interesting topic.
Cool. Yeah, it's an active area. 3D printing. Yeah. Okay. Yeah. Okay. So it's time to go to the lab, I guess, right? Would be nice to see it.
Yes, sir.
It's time to go to the lab.
Yes.
Yeah.
Yeah, we'll try.
We'll see it. Yeah. Yeah. Okay. Then see you tomorrow. Don't be late. Too much.
Okay. So try to come as soon as possible. Because again it is stretching, na? So unnecessary the last it is stretching like today it is half an hour late. So we have only after half an hour.
Okay. Shall I give it to you?